Well, hello. I'm back after a while. And as you can see, there's Lego here, and as you can remember, I originally said I was gonna use a PC power supply, but yeah, that went to shit. And Lego is just more versatile, to be honest. You can make more with it, and you don't need to waste a bunch of glue like I've done anyway, so rip glue. But yes, lots of things have happened and changed. And software wise, the first thing is that software PWM isn't really accurate. Let's just put it at that. And if you'd actually tell these servos here that drive the wheels to be centered, they'd actually just twitch the robot because of the inaccuracies of the software PWM, especially under the heavy loaded, well, not heavy, but medium heavy load it's getting from the task of compressing the video from this webcam and well, dealing with Wi-Fi and stuff like that. What's more change? Yes, apparently well, to my knowledge, there isn't any driver for this particular webcam which supports the microphone in it as well. So I have an external microphone right over here. Now the video works, but no audio, as I said. And this microphone is quite shitty, and I still haven't fully configured it. And every time I turn this thing on, I have to manually log in and open Alsa Mixer and well, basically turn up the gain, because otherwise you can't hear shit. And this speaker here, it's actually been through iterations. At first it was this, but it was quite obvious this small of a surface isn't enough to make, well, audible sound that can be heard in a medium loud environment like everyday life. So I first started by putting in this thing right here in the front, this black thing. It's a headphone amplifier, and it has its own battery, its own charge protection and all stuff like that, and its own volume and on and off. Here, I can actually turn it on. There, it's on. You might be able to see it. It's actually blue. And I'll turn it off. Now it's off. So yes, but that wasn't enough. So I then moved on to having a larger speaker with the headphone amplifier, and this works quite well. If I bump up the volume on this thing to maximum and on the Raspberry Pi to maximum, it's actually quite bassy, and it actually makes quite a lot of high-pitched noises as well. So yeah, that's acceptable. Now, the routing of all these wires is, well, let's just say suboptimal at best. And underneath here, here's all the cable for the camera just looped in there haphazardly, and the speaker's just resting on two knobs, really, which you have to get kind of precise. There, now it rests on these 2 points and a point underneath of here. And there's also a roll of tape here attached to the back for extra back weight, so it can actually sit back on its follower wheel. Speaking of that, the follower wheel it's actually quite a big follower wheel. It's made out of a 4x2 piece and 5 across axle, and some spacers and a converter to get it to an axle in the other direction, and then you got the actual wheel. Now this wheel is, let's just say it's not what's the name? It's not symmetric when you look at this and that side, but that doesn't really matter because those two are lower than these two right here, which focus are the same height. So that's actually symmetric. These two, not the outer ones, but the inner ones are actually symmetric. So that's not going to cause any like stress, I guess. And that's mostly the mechanical stuff. There's the claw here. I built and added this yesterday actually, after seeing a post in the Let's Robot Discord, shortly after joining it, might I add. So, great resource, let's just say that. And my problem now is that I need to drive this, and this is the only Lego motor I have like left. So luckily I've already modified it to accept standard blue cables that I have just laying around. So if you apply a voltage here, this thing will open and close. Actually, let's do that. And I'm gonna set the power supply to roughly 4 volts, because that's in the end the voltage roughly we'll be using, because that's what we'll have left after we've built our H-bridge. There you go, closing. And that's about the final speed it will move, hopefully. And this power supply is also limited to the maximum current of the circuit I've built. I haven't built it yet, but I have it simulated. But yes, let's demonstrate its grabbiness, I guess. So let's jam it in. It pulls 800 milliamps. That's about as much as my circuit can do. And these are actually really tight now. I can get my finger in there, and if I get my finger in here, I can actually pull the bottom along and stuff. But that doesn't really say anything. But they snap together. What's more? Yeah, not much really. What we're gonna do is, because of this bot's power supply, it only has 5 volts as its maximum voltage, so we don't have a lot to play with here. And we're gonna need some sort of driver that can drive this motor in both directions, as you just saw. Now, either, and what I kind of hinted at there with the 5 volts is due to why I have this here. This is a, oh, what the F is it called again? It's a 98, 88, 92, 88 something, A92 something. What the, I need to check this now. Hell. Demonetized. Let's say A92, no. A4988, yes. That's a really common stepper motor driver. And you could actually use this to drive these motors here, or this here, if you were clever enough with your half stepping and your enable and reset and stuff like that. However, this thing requires 7.5 to 8 volts to even have current flowing in the coils. I don't have that on this, so out of the question. And then I was like, well, maybe I can use batteries or rechargeable batteries or alkalines, or who the hell knows. But then I was like, let's just build our own H-bridge. But then I remembered, I don't know how transistors work in the slightest. F. So, follow me as I walk over to the computer, and we shall go through some transistor logic and how I, well, figured it out to be so far. So here we go. Let's go to the Wikipedia for bipolar junction transistor, because that's what we're using here. We're using we're gonna use 4 NPN bipolar junction transistors for this H-bridge. Why 4 and not 2, and mix in 2 PMPs as well to make the logic easier or wiring easier? Well, I don't have PMP, so that's out of the question. So we're forced to make an H-bridge with NPN transistors. Now, what I didn't really understand about, this is really good for illustration. What I didn't really understand about transistors before is that they are a current controlling device, not a voltage controlling device. It controls current with current. Now that's something I had the wrong way around for many years, and quite frankly I burned a lot of transistors that way. But now, with that knowledge, and also with the realization that all bipolar junction transistors like this one is, if you look at it, contains p-doped silicon and n-doped silicon between 2 leads. What do we have here? It kind of looks like a diode. Now, what is a diode? Diodes, simply put, allows current one way and not the other. And that current, in turn, will result in voltage not being able to come from one way and go the other, or vice versa. Now you could read all of this for yourself instead of me just scrolling up and down and making you mad about it. But what we essentially gotta realize here is that bipolar junction transistors essentially contain parasitic diodes. So these NPN diodes, transistors I have here, are essentially 2 diodes in a package when you think about it. Now, and those 2 diodes are squished so tightly together. Now this distance here should basically be none if it's an actual transistor, because what side of the diode is P oriented? Okay, screw that. Let's just the silicon. If the silicon on this side is the same as the silicon on this side, essentially you have, well, instead of a triangle, you have 2 triangles butt up together. You'd imagine that their silicon on this end and this end are basically gonna be the same. Now, if that happens, some magical properties happens with that piece of silicon in the middle, which allows transistors to do what they do, which is to amplify or switch current. So, with that in mind, let's design a H-bridge driver for 5 volts. Now this is something I found by just literally searching circuit simulator and going to this FileStud whatever thing. Maybe they, well, scrape my design or whatever, but I don't fucking care. This is just to rough stuff up. So this is a circuit simulator which allows us to do some stuff. First of all, we're gonna add a voltage source. That's our 5 volts. Now, to our 5 volts, wait, we shall also have some kind of ground in here too, right? So let's add a ground. Add ground. You can just add a voltage source with 2 terminals, like this one, which is essentially a battery, but that's no fun. Now, what we want is our NPN transistors, and I got that by just hitting the N key on the keyboard for NPN, and I hit space there, which allows me to go into drag mode. So, with this in mind, we shall flip this over, and we're gonna lay out a classical H-bridge formation thing here. If you want to, you can space this out. I'm probably gonna space this out just to make it very clear what the hell is going on. Essentially, I'm gonna move stuff around appropriately. And we're gonna add a resistor, which you could get by just doing R, but I haven't learned this really yet. But yet I knew that, but not in time. What we need now is an inductor, because our motor is a form of inductor. So we'll go sort of centered, and I've measured the resistance of that motor, and it's roughly 50 ohms. And it's definitely not 1 Henry, but we'll put it at 0.1. No, actually we'll put it at 10 millihenry. That's a bit too much, but whatever. And let's start adding the wires. So, here we have a circuit. Here we have a H-bridge, basically hooked up to 5 volts and ground, and there's nothing on either inputs, but there is current flowing here, around 20 picoamps. Not a lot. That's just because of how, well, I'm not gonna get into it, but there's forward and backwards biasing and all that kind of stuff, and it's weird. Silicon is weird, but let's try what everyone says you should do, which is have a resistor to each. Not same size, I am not amused. So no fast way to duplicate, rip. So this is the usual configuration, maybe? Let's add 2 resistors and edit them to be 250 ohms. Just roughly the... Actually, fuck. I just realized we're using a Pi and not our Arduino. Our Pi, GPIO, current limits. Yep, it's gonna be like total 51. 3 milliamp per GPIO pin. Wait, maximum 16 milliamp per pin. But 3 milliamp is stated. Okay, whatever. Seems complicated. So. $16 milliamps. We need to convert that to a resistance. So we have ISV over R. And we want R. So we do 5 volts over, what was it, 16 milliamps? $312 ohms. I'm just gonna copy paste that because, oh come on, because I am lazy. Also, this only works on a regulated power supply without any resistances before it. So ideally it doesn't at all. Just so you know. Wires, no. Switch. Let's open these switches. Okay. So here we see oscillation within the inductor. That can damage the resistors. 5 volts, negative 200 volts. Yeah, that might definitely hurt a 40 volt resistor. So let's mitigate that by putting in some diodes. And immediately by putting in one, you see I'm transferring current around differently. This goes in, that changes 2, and now it should actually start to dissipate. Now this transistor here is only seeing a collector emitter voltage of 300 millivolts and 1 point something volts, it looks like. I have no idea. It's too fast. Anyway, let's turn this thing on. So here we have a transistor. Wait, let's just check the current we're pulling here. 50 milliamps. Quite bad. Not good, not bad. And we are wasting about, no, we're using about 132 milliwatts of power in the motor, and the original circuit is producing 272, so we have some losses in there. Quite a bit of losses actually. Yeah. this transistor right here has a voltage drop, a collector emitter voltage of about 2.3 volts, and it's in the linear region because it is not saturated. Now, why is it not saturated, you might say? Is it because of the resistor? Well, let's try it. And as it seems, no, it's not. We're still in the linear region, and we still have about 1.87 volts across the transistor. Mind you, it's better, kind of. We have a lower collector emitter voltage. We're still pulling 113 milliwatts, which is, well, almost half of the load current. So a lot of energy is wasted in this transistor right here. And that's gonna switch over if we do this side instead. So now this one is gonna start heating up. Ugh. Now, how do you solve this? Well, the way you solve this is that you make your base voltage higher than your collector voltage relative to the emitter. Now that seems weird. Well, that seemed weird to me until you realize that it's a current control device, and if you have a higher voltage, you have a higher potential for current. So that's going to obviously saturate the middle silicon, obviously. Well, I say obviously, but it's not going to be obvious to a lot of people. Why am I even trying to explain transistors? It's a thing I barely even know. But yes, to fix this, we need to ensure saturation. And to ensure saturation, we need to make sure the collector emitter voltage is lower than the base emitter voltage. How can we do that? Quite simply, we could add a resistor, because if there's a current running through it, there's gonna be a voltage drop. Yeah, 50 ohms. Okay. Now if we run this circuit, you're gonna see that we have 7 milliwatts across this transistor, and it even says right there it's at saturation. Now our load is pulling 115 milliwatts with a current of 48 milliamps. Now load is pulling 48 milliamps, but we're pulling around 51 milliamps. It's quite a bit, actually, quite a bit of difference. 3 milliamps, 47. Okay, because it was close to 50, it threw me off. But yes, that seems correct. So, also, just to make sure, we're putting 3.77 milliamps, which is not a lot. We might even be able to just replace this with a wire and we'll have 6 milliamps still, which is way underneath the minimum. This is the ideal way to actually know. Moreover, like, I guess that feels more like an accurate representation of a GPIO port. 5 ohms. Actually, let's check that. RPI, GPIO, ohms to ground. No, that's not. Well, I'll just leave it at that. It's not ideal, but it's close enough. That's good enough for me. But yes, this sort of works. I mean, you could keep pulling this down, like pull down to 10 milliohms, 10 ohms, and check if you're still at saturation, which we aren't. So we pull it up to 20 ohms, and we're at saturation now. We're at saturation down here, so yeah, you could do that. Or you could just say, F that, I have diodes, and just do that and be done with it. Because diodes are inherently gonna drop 0.6 of a volt whatever current they have running through them. So, and you don't get, well, so you have a fixed voltage drop essentially, which enables you to tune the resistors right here much more finely than you would be able to do, and it would be much less voltage dependent, I'd say. It would be more stable, I think. Not completely sure, but I'm fairly sure. So let's, first of all, let's just try and replace this with wires because I'm stupid. And let's see how much that pulls. 4 milliamps. And we are at saturation, and we are pulling 9 milliwatts. And this is pulling 10 milliwatts. And our current load is pulling 346 milliwatts. So that's actually quite an improvement, I'd say. And we're passing 87 milliamps, so almost 90 milliamps. So, I mean, we could go back here and tune it until it's just saturated, but in a way that's counterproductive because saturation isn't really saturation. What I'm trying to say is that saturation is not the definitive limit. If you have reached saturation voltage relative to the other pins, and given that you're over the diode threshold voltages, fuck, I lost my train of thought there. Yeah. That sucks. Really, what the? It's there and then it's just not. What happened, brain? I hate you, brain. Yes, you could tune this like just into saturation, or you could like see now when we have a 510 resistor here and we're still at saturation, but we're wasting 33 milliwatts on this transistor right here. If we remove this and replace it with a dead short, sure, we're pulling more current through the base here, about 4 milliamps instead of, oh, what was it before? Before it was 700 microamps, 750 microamps, so it's quite a bit more now. But since we've oversaturated so much, we've dropped from 33 to 9 milliwatts of wasted power in the actual transistor itself. Now, is that worth the extra milliamps through this here? What's this? 496, and that's the base voltage here. Let's see. 496, 496. The DS. Yep. Essentially, once you've reached saturation, it's kind of an arbitrary point that humans have defined. I'm kind of just pausing there just to be ironic because everything is defined by humans, but whatever. I forgot my train of thought again. What the? Brain, could you please stop this? I'll just click around until I get that thought back. The entire circuit pulls 87 milliamps. Load gets 83 milliamps. So the difference there is what's pulled by this, which is 4.63 plus 4.2. So the currents here are actually quite well matched. And why I have resistor down here and not up here is because up here we're switching between 4.3 volts and 4.2 volts, which is quite high up, and down here we're switching between 8.5 volts and 0 volts. So we're switching up at the top end of the pressure scale and down at the low end of the pressure scales, and to switch the higher pressure we need to give it more pressure, so we just give it, well, we give it unrestricted pressure essentially, and down here we restrict the pressure to not blow this the fuck up essentially and make this into a base emitter runaway like that, which can happen if you don't have that. As you see, it's just running. Well, if the pin was able to sync the 800 milliamps, which it isn't, I'm just gonna say that if it was able to, but it's just gonna sync it through the base emitter because of that parasitic diode in there. That's kind of part of how you can think of a resistor. It's two diodes, and the one pointing to the emitter magically interacts with the one pointing to the collector and allows it to be backwards biased quite easily. That's essentially what it is. And there you have ringing. That's left. Why isn't that dying out? Oh, because I have that there, I guess. So it seems like 1K down here is, well, fine. Are we at saturation? We are at saturation, and here we are at saturation too. So we're actually at a bit lower saturation down here than up here. But if you want to, you can change this to 510 and there you go. Actually, we're pulling more now. We're at 11. So the power output does not equal the amount of saturation, by the way. That's just a good general reference. 750. 10. Let's try 1.2K. Let's try 2.4K. This is interesting. Where's my K? There it is. 10.9. So this one here at the bottom doesn't really matter, as long as you restrict it so that the parasitic diode in here doesn't really just short the supply essentially and burn itself up, because that's what it's doing when you have that. Let's see what the base emitter voltage is. 780 millivolts. That's almost a volt. At a current of 16 milliamps. Oh, what a coincidence. So 6 ohms is it's gonna be plus whatever the resistance of this. No, but it's in saturation, so base emitter voltage a volt. It's still dissipating half a watt. So that's, yeah, that's half a watt. That's quite a bit too much actually. But anyway, let's edit that back to 1.2K, because I think that's what I have. Let's change this to 1.2K. And also let's change the transistors here so that they are of the same characteristics. And my transistors have a amplification rate of 200. Well, it's actually 222 or 231, I think it was. But I'm just gonna say a bit lower at 200, just to make up for other resistances and random shit and parasitics elsewhere. So these transistors are essentially the ones I have on the bench, which you can't see. Yeah, it's up there by the claw to the right, by the screwdriver. It's a very, very small package, and I think that package is rated for a watt, maybe it's only 250 milliwatts actually. So let's not try and push these too hard. The fans in my computer is now turning on full speed, which tells me that the heat in here is reaching some ungodly temperature. Yes, it's 30 degrees in here, fuck. I was afraid of this. So let's just continue. Let's just ignore it. Yes. So with this design, we can get 80 milliamps flowing through this motor at, what do we have here? 4.16 volts. And that's the parameters I used before. And this is how I got them, essentially. Really super duper easy. Now it's just to make this and program this and make it work. Also, short circuit voltage in case of failure is 1.3 amps. And most of that power is okay, the top transistors here are in saturation, so they're gonna be okay. They're just dissipating 7 to 8 milliwatts. These, however, these take the brunt of the force. They have a collector emitter voltage of 4 volts. Dissipating about 2.79 watts. 2.8 watts, yeah, that's very nice. That component is gonna get very hot, very fast. Let's just see. Let's just stop at that. And that means my top transistors are gonna be okay, while my bottom ones are gonna bite the dust. I could lower the resistance here in order to mitigate that, I guess. This is gonna make the circuit less efficient, but it's gonna drive the motor at higher current. Now it's driving it at 91 milliamps. But the short circuit current is also gonna be a lot higher. It's gonna be a lot. Actually, it's the same. And this actually no. 3.17 amps. I don't think that's what it was before, but whatever. And this transistor is now dissipating about 6 watts. So yes, that's not gonna work. Could do 2.4K here, see what happens. We're now dissipating 1 watt during fault conditions. And if we go down to 1.2K, I'm essentially just paralyzing up resistors here, or going down the regular value chain that I have available to me. So this is actually a bit worse. Full condition current just under an amp. That ought to be enough to mildly brown out the RPi, I bet. Still on saturation up here. Perfect. Let's see what's saturation down here. Only 11 milliwatts. So 4.8K or 5K is good enough for 5 volts, it looks like, with a 50 ohm load. It's important to remember the load is dependent, well, the circuits here and these two resistors kind of depend on, and if you have any resistors up here too, kind of depend on your load and how it responds. So if we make this load like at home, good the fucking luck is all I say. I mean, we're still pulling 20 milliwatts on this transistor and 700 milliwatts on this one, so almost an amp again. This isn't even full conditions. What the F? My screen is flickering, that's concerning. So F, what's that, 9.6K? Quick maths, probably failed. Yeah, who the fuck cares anyway? Wait, that was wrong. Spare lower to 4K and not saturated. Let's try the lower one too. Not saturated. Let's try the 510. We need a resistor up here. Yeah. See, if you load this low enough, you're gonna need resistors up here too. But my load is 50 ohms, so I'm not gonna have to deal with that sort of shit. So back to 4.8K, and let's test the circuit and let's build it. I might actually pause right here to cool down the room because it's actually getting quite unquestionably hot. But as you see, this bridge driver works. What happens if we say that these are 1 ohm? Fuck. I don't want no scopes. So we are at saturation, and we're at saturation 11 and 12 milliwatts. So, not a bloody fucking difference. So essentially, if we go back to this image again, if you think of a transistor as this, and at the same time as this, by essentially tacking on the diodes as parasitics, you can pretty much follow me along that you pretty much need resistances in front of the base to limit the current going from the base to the emitter, because there's a diode between there. And that's whether or not you're using an NPN or PNP transistor. Because with an NPN transistor, you're going to turn it on with positive voltage, and the positive voltage you apply to the base is going to inherently, by the way it's laid out like this, going to leak out through the emitter. So you need pressure regulation, I guess, of the base to not basically drive the base emitter voltage, base emitter currents too high, because then you can fry the thing, and then you're risking damaging stages before this if this is pulling. Like, say if this was like shorted and it became a ohm, this transistor here would burn up pretty quick. I mean, it's just by its power right here, it's pulling 1.7 watts. But that's heat damage, but it's also gonna have electrical damage over time, I think. I'm not certain, but I'm pretty sure. So, if possible, avoid fault conditions, and yeah, you shouldn't rely on the, well, you can rely on the parasitic diodes as safety diodes for this coil if you hook this thing up in a very specific way, by having the base of this side hook into the load on the other side and vice versa, and that way you can create a run-going loop here in the bottom, which allows you to use the parasitic, well, diode to basically dump the charge back into the inductor and have it, well, discharge itself without going back to the voltage source as this thing does right here. I can actually show you that if I slow down the speed fast enough. So if I open this, or what? Okay, let's just make this a Henry. There you go. Oh god. Going 83 milliamps. Yes, we're at peak, I guess. So now when I open this, the current in this inductor is gonna want to keep going, and it's gonna keep going whatever this other circuitry wants to or not. It's basically gonna start shoveling electrons across against their own will and build up pressure, aka voltage, and it's gonna oscillate back and forth. And this circuit doesn't really show it for some reason, but maybe it's because of the resistance I have in here. Come on, girl. 170 milliamps, oh shit. So now we're going quite fast, and I'm gonna open this. Why? This worked before. Okay. Whatever. I'm not even gonna bother. Ooh, what was that? A Henry is quite big. I'm just gonna say that. Actually, yeah, why not? 4.1 millihenry. Good random value. Why isn't this? Oh. Well, that would have been good to know before. I thought that wasn't like a glitch in my screen before. Like, is my shit about to die? And yes, this is actually a versatile piece of software, and it's all running in JavaScript, I think. Canvas and stuff. Yeah, it's a canvas at least, so you can do a lot of with canvases these days, and HTML5 and all that stuff. Amazing. But yes, here is the design that I've somehow gotten to. Wait. How many volts is this? Yeah, how many volts is this? 4.40 volts. I can't really. I have to put 4 diodes in at least in any way. So that kind of sucks. But hey, we can put them in clearly like this, so that everyone understands what we're all about. And I don't think it's doing jack shit. It stops so instantly. What? This is. It's something. Something is wrong here. Hey! Something is wrong! MF. That's not how inductors work. F your trapezoidal approximation, whatever the hell that is. I just want the normal inductor random, well, not randomness, what's the word? Behavior, yes. And we're up to speed and shit. Is it that fast? I'm gonna check these and see if they're pulling current. Well, they're just experiencing voltage so far. Properties. I don't want voltage, I want current. Properties, nope. Properties, nope. Properties, nope. So let's open it at a slow simulation speed, which is basically one step above 0, and do that, and F all happened. Nothing went through the diode. 4 Henrys. Okay, again. Can I... Why is it so hard to show this? Oh. Balls. That's why. Yeah, that would explain it. It's because of this diode right here. Let's just add another diode in the other direction. Fuck. Hell. Two 100 millivolts, 100 millivolts. Actually, no, it's 100 millivolts. 50. 20. Let's open it. There we go. That's what I wanted to show you. I was like, where's the backflow from? But it's kind of obvious that without that, this diode would have just said bye-bye. Because it would probably have been subjected to about 200 volts or so. But to be fair, diodes are very ruggedized these days. So a normal 0.6 volt diode, nominal spec 40 volt, can probably survive spikes of around 600 volts. I don't take my word, but diodes are very robust these days, and that's why they're used to do this suppression. So there's, but I don't know, this might have been cooked, or something else might have been cooked, or downright actually, maybe a transistor if you were changing direction very fast, so that you actually got caught in that, and it somehow overloaded the base emitter backward bias. I don't know. But that's kind of my understanding of transistors now, is that they're basically this with this on top, or this with this drawn in as parasitics. So yeah, I think I'll take a pause now and cool down the room somehow without making all of the insects get in here. I think I'll just turn off all the lights and evacuate, which is not really a good condition to make a video in. God, brings me flashback of freaking Minecraft Let's Plays when people would go into caves and be like, oh, sorry guys, you can't see because it's so dark, or YouTube video compression. Or maybe just, that's just from there I am from. Damn it. But yes. This robot right here, oh, F. There. This robot right here is currently not live on Let's Robot.tv, but it will be once that claw is working. And it will be after the second stream I'm gonna do. Either today, like soon, or tomorrow. because quite honestly it's late. And to be honest, I just realized that's basically the purpose. I just fucked up everything. This was basically an update video. Oh, and apparently the chat has been active, and I missed it all. Wait, we have 3 viewers at one point? Yeah, let's not dabble over statistics and stuff like that, but that motor and that claw is what's on my agenda. I aim for it to be controllable with 2 pins essentially. 2 more pins of the Raspberry Pi. Controlled in unison to not short out the power supply, but yeah. Maybe I can get it to actually close and grab onto something. What about this? Yeah, that's fully closed. Oh god, this bot is gonna be so annoying. It's just gonna take stuff and just joink, pull it away and just drive away with it. And let's open it. Wrong way. Yeah. Could it actually like grab something? How about this piece of paper? Grab it. Well, it grabbed a piece of paper. I say that's enough success. Well, enough for us to tear the paper. It was at a soft spot, a weak point though, which is expected. But here's like the circuit board I started doing, and then when I plugged the leads in and did everything and hooked up the signals, nothing worked, and I was like, fuck this, I'll just simulate the thing and learn a bit more about transistors while I'm at it, and well, it seems to have paid off. My entire view on transistors has been changed. To me, now they're just diodes with special properties. And with that said, I'll see you soon in the next one.